Here is an example of thin film interference problem. So let's read it together. An oil film with an index of refraction of 1.45 floating on water is illuminated by white light at normal incidence. All right. The film is 280 nanometers thick, and we want to find the dominant observed color in the reflected light and the dominant color in the transmitted light, and we have to explain our reasoning. All right, so what we have is we have some air. Let's change the pen to something more substantial. All right, so again, we have air, we have oil, and we have water. Now, water has an index of refraction smaller than that of the oil. All right, so let's put the surfaces here. Okay, so here we have that's air. Air has an index of refraction of 1. This is oil, which has an index of refraction of 1.45. And this is water, which has an index of refraction of 1.3 or something like that. Okay, so let's start. I'm going to try to use different colors just to make sense a little bit of this. So we have a light coming. All right, this is ray number 1. Then it goes through. This is ray number 2. Then it comes back. This is ray number 3. Then it transmits. This is ray number 4. And this is ray number 5. All right. So we're interested on ray 4 and 5. And on the other hand, what we have, and I'm going to do them in different color, we have this one that transmits here, and this one that transmits here. And of course, you see that this process can keep going, but we're just interested in the first set. All right. What else is given to us is the thickness of the film. All right. And the N. So the T, which is 280 nanometers, so 2.8 times 10 to the power of 7 meters. Okay, so the light is white. We want to know what is a predominant, which means what does it mean, the dominant observed color? It means which one will give us constructive interference. And the same here, which one will give us constructive interference. So if we have a diver and he's looking, he would see things in that color. If you have somebody up here, he would see the things on that color. So when we say that, we're actually looking for the lambda. All right. So we're looking for the lambda. So let's start. What we want constructive, recall. Okay. So we have 5 and 4. So let's start with 5 and 4. Remember, we want to know whether they are in phase or out of phase. We're looking for a constructive scenario, constructive interference. All right, and we're looking for the wavelength. All right, so we are going from low to high index, right? So we're going from low to high and then to low again, right? From air to oil to water. So the 1 and the 5 are out of phase. All right, so let's record that 1 is out with 5. Okay, the 1 and 2, of course, are in phase. Now the 2 and the 3, since it's going from high to low, they are in phase. All right, so 2 is in with 3. And you notice here that 3, we know that is in with 4. So if you compare all of them, you realize that 5 is out of phase with 4. All right. So these two waves, these two rays are out of phase with each other. in order to have that constructive interference, we have to correct that out of phase by half a wavelength, right? So in this case, we have 2t equal to half of that lambda n, which is lambda over n, right? The lambda in the medium. So we're going to solve for lambda to be 4 t times n. All right. And if we do our calculations, we arrange pretty much for lambda. We have 4 times 280 times 1.45 is 1000. So it's 1624 nanometers. All right. However, sorry, what we're finding here, my mistake, we're finding the lambda, right? And then we have to divide it by, so lambda that we're finding is 4t. So lambda that we're finding is 4 times 280 is 1120 nanometers. All right. And then we are going to divide it by 1.45. So the lambda that we're looking for, remember, this is a lambda in the medium. Now we're looking for the lambda in vacuum, because that's what we're going to see when we are in air. Is going to be lambda m over n. So the lambda in vacuum is going to be 772 nanometers, which is, I'm guessing, red. So now we are going to, it's high wavelength, right? So it's kind of red. What we're going to do now, we're going to find the same way, we're going to find the transmitted one, okay? So let's call them 6 and 7, okay? So 6 is in phase with 2, 7 is going from, it's reflect from high to low, is in phase with 3, and 3 is in phase with 2. So 6 and 7 are in phase with each other. 6 and 7 are in phase. So which means to have a constructive interference, 2t has to actually be just equal to lambda. All right. So we find the lambda to be 2 times 280, and that is 560. 560 nanometers. And then, of course, to find it, the proper one, we have to divide it by n. So the lambda is going to be 560 divided by 1.45. That is 386 nanometers, which is more toward blue, as we would expect. Okay, so this is somewhat long a question about a thin film interference.